Welcome everybody to this mini-series on measurement-based quantum computation. Measurement-based quantum computation is a computational scheme driven by measurement, by local projective measurement. Everybody who is watching this video probably knows the circuit model. It's a very famous model of quantum computation, and the circuit model is driven by unitary operation. Measurement-based quantum computation is different in this regard. It is driven by local measurements. And that's what we're going to talk about. So what you see here is a cluster state. Cluster states are very important for this lecture. Cluster states are states of qubits living on a grid that are entangled in a particular way. So every dot that you see here in this image represents a qubit. And you see that these qubits are connected by lines. These lines form a grid. And that grid represents the way in which these qubits are entangled. We will talk about that more. But these entangled qubits, entangled in this cluster state fashion, they are a computational resource, and that shows up in many ways. So let's look at the first example of this. What you see here is two particular qubits labeled A and B, and they can be very far away from one another, they can be very close to one another, doesn't matter. So suppose we want to entangle them in a maximal way. Maybe we want to put them in a Bell state. We can do this by measuring individual qubits on this two-dimensional grid in specific bases. And that's what you see here on this image. You have qubits measured in the eigenbasis of sigma x and qubits measured in an eigenbasis of sigma z, and those form a tube that ranges from A to B. After these measurements, those distant qubits A and B are prepared in a Bell state. So cluster states allow you to create entanglement between distant qubits by local operations. So that was the first example. Now let's look at another example. Again, we are starting with this two-dimensional cluster state that we will properly define later. And next thing we do with it is create a code state, a state in this so-called surface code. It's an important code in fault-tolerant quantum computation, and we get such a state by measuring half of the qubits in the cluster state. So these are the qubits shown in black and red here in this figure, in this checkerboard fashion. So we measure all those qubits, and the other half, the qubits remaining unmeasured, they are now in a state in the surface code. So how far can we take this? Maybe the funniest thing that we can do with two-dimensional cluster states is use them for quantum computation. So these 2D cluster states, they form universal substrates. Any quantum algorithm can be implemented on them by local measurement. This is a universal scheme of quantum computation. And now you may ask, what about fault tolerance? Can we do fault-tolerant quantum computation too? Yes, we can. And for that, we need to go one dimension higher. We no longer talk about two-dimensional cluster state, but three-dimensional cluster states. And we will talk about that as well. So this is now the outline for this mini-series. It has 4 parts after this overview. The first part will be dedicated to computational universality. Second part to fault tolerance. These 2 aspects were already mentioned. And then there are 2 more parts. The third part is on quantum computation with probabilistic gates, which is particularly applicable to quantum computation with photons. And really, measurement-based quantum computation has taken hold in the photonic community. So it fits hand in glove with the experimental capabilities you have there. Part 4 is a more theoretical exploration It's called Computational Phases of Quantum Matter, and that's a subject between quantum computation and condensed matter physics, and an exploration into the question of what the role of symmetry is for quantum computation. This is now the outline for this overview. I will tell you roughly how the scheme of measurement-based quantum computation works, although we will go into that in more detail in the upcoming lectures. Then I'll talk about cluster states, and I tell you a little bit about the experimental side of the field. Okay, so let us start to explain how measurement-based quantum computation works. Let's begin with an introductory remark. There is two different evolutions in quantum mechanics that are very distinct. There's unitary evolution and there is quantum measurement, specifically projective measurement. That's the extreme case. Yeah, and these two evolutions are very different. Unitary evolution is deterministic and projective measurement is probabilistic. So in measurement, we have typically live with the measurement outcome we got. We cannot choose it, and after the measurement has taken place, we cannot go back to the state before measurement. So measurement is probabilistic. Also, unitary evolution is reversible. Measurement is not. So very distinct evolutions, but from the perspective of quantum computation, they amount to the same. You can implement universal quantum computation using unitary evolution, that leads you to the circuit model, or you can use it, you can implement it using measurement. And that's what we are going to talk about today. That's measurement-based quantum computation. So here is the computational scheme in a nutshell. What you see in the image is a two-dimensional cluster state being measured. So every symbol you find there, an arrow or a dot, represents a qubit. And the symbol decides the basis of the local measurements. So the arrows represent measurements of the eigenbases of sigma y or sigma x or anything in between, and the dots represent measurements in the eigenbases of sigma z. And they have different uses in the computational scheme. So when you remove the qubits that have been measured in sigma z, you find a network arising that already looks quite a bit like a quantum circuit. And indeed, this is how the universality proof is done. You map it back to the circuit model. So let me summarize the most important things that need to be said here. So, of course, not every entangled quantum state works for this computational scheme, but the cluster state is such a universal resource that you can implement any computation on it. It's not the only one. There's other states out there that do the same. So, for example, the AKLT states familiar to condensed matter physicists. So, from the computational perspective, what's going on here is the following. So information is written onto this resource state, processed on that resource state, and then read out from it again by 1 qubit measurements only. And we will look at that in greater detail later. Let's now proceed to describe some characteristic features of measurement-based quantum computation. The first feature is that measurement-based quantum computation, and it's certainly not an advantage, measurement-based quantum computation is hungry for qubits. So when you look at this figure here, you have the cluster state with all the qubits present. So the first column is for the logical quantum register in its input state. So that's the qubits you would have in the circuit model. But then you have all the other columns next to it, and they represent the quantum register at later times. In measurement-based quantum computation, all these qubits need to be provided at the beginning. So you have to use more qubits than in the circuit model. Now comes a qualification to what I just said. So you can make measurement-based quantum computation more efficient. You can reduce the qubit count to maybe twice of what you have in the circuit model. if you want to. And it goes like this. So here you have your cluster state. Here you make it longer by entangling more qubits in it. And on the other side, you make it shorter by measuring the qubits. And after the measurement, the qubits are disentangled, they are released, and they can be used again. Yeah? So you get, in this way, in this conveyor belt fashion, you get by with a much smaller number of qubits. And that's indeed used in some implementations. Let's remain more abstract for now. So measurement-based quantum computation is really the scheme of choice when you talk about quantum computation that use entangling gates that are probabilistic. That is, you have entangling gates that sometimes succeed and sometimes fail, and they tell you when they do what. And that is the case for photonic systems. So in such a situation, measurement-based quantum computation helps you reduce the operational overhead very significantly. So this builds on the Knill-Milburn-Laflamme scheme of quantum computation with photons. So that was a very significant step. It removed the necessity of Kerr nonlinearities and replaced them by measurement. And if you use measurement-based quantum computation on top, you can be much more resource efficient. And we'll talk about that later too. So now an algorithmic application of measurement-based quantum computation. So the little person there with a hat, well, let's suppose that's you. You have a quantum modem, and your quantum modem, because it's an early generation model, it's all that's currently available on the market, is a modem that can prepare individual qubit states and send them out one at a time. That's all your device is able to handle. It can send qubits out, receive qubits, but only one at a time. It can only hold one at a time. And with this very limited hardware, you want to let powerful quantum servers, which are around, you want these servers to compute for you. However, you do not really trust these servers. So you do not want these servers to learn what you are computing, and also you want to verify them that they do indeed compute what you want them to compute. And this is possible, and this scheme of computation has been discovered in the framework of measurement-based quantum computation. So this is the first algorithmic application of the scheme. Final point that I would like to make here relates to fault tolerance. So three-dimensional cluster states are very well suited for creating entangled resources fault tolerantly across large distances. So they do something like the quantum repeater does for you, but they do it somewhat more efficiently. Yeah, and about all these error-correcting properties we will talk a little bit later here in this series. So now let's move on to cluster states. So cluster states, we talked about them already. They form the entanglement resource for this computational scheme. So it's time to talk about what they are. And before we formally define them, let's talk about a way in which they can be created. So to get some initial understanding for what we are dealing with. The creation, or there's just one possible creation procedure, maybe the simplest one, has only two steps in it. And it's just these two steps irrespective of how large these states are. The first step is just preparing each individual qubit in a superposition of the 0 state and the 1 state. Superposition of spin down and spin up makes it an eigenstate of sigma x. So every qubit is prepared in this fashion, all in parallel. That's the first step. And the second step is an interaction. It's the Ising interaction, in fact. So we switch on the Ising Hamiltonian, sigma z coupling for all nearest neighbors for a finite amount of time, so a very specified amount of time, and then we switch it off again, and then we have the cluster state. And important to note is that the interaction time for the Ising interaction is independent of the size or dimension or geometry of the state. It's always the same. Yeah. This is how the cluster state is being created. Okay, so let's take this apart a little bit. Let's see what this leads us to. So what you see here are three examples of small cluster states. So the first example is really the smallest possible. It's the cluster state of 2 qubits. And it is a state that you already know, namely modulo local unitaries. This is just a Bell state. Slightly more complex example of 3 qubits. So if you take the 3-qubit cluster state of 3 qubits in a row, that is just, again, modulo local unitaries, a Greenberger-Horn-Zeilinger state. That's a state very well known in quantum foundations. Well, and it is the state that also carries the name of Schrödinger's cat. Final example here on this slide, slightly more complicated geometry. So what you see here is a cube with one vertex removed. So the cluster state on that arrangement is a state in the Steen code, 7-qubit Steen code. And this example is important because it shows you that cluster states are related to quantum error correction, and we'll make a lot of use of that. All right, now after we've seen the examples and the creation procedure, let's proceed with the formal definition. Of course, we could take the creation procedure as the formal definition, but we'll see that the definition that is given here is actually quite useful. So cluster states are stabilizer states. So for those who are not familiar with the notion of stabilizer states, they are defined in this fashion here. So they are eigenstates of a bunch of operators. So the cluster state, denoted as ket C, is acted on by an operator Ka, and that action reproduces the cluster state that you started with. So the cluster state is an eigenstate of this operator. And so it turns out if you choose a sufficiently large number of such operators, then all these eigenvector-eigenvalue equations uniquely define the state, in this case the cluster state. So what remains to say, and this is now the cluster state's specific part, is what these stabilizer operators look like. And this is shown in the figure. So the label A that you have here in this operator Ka is actually a site label. It labels a site in the lattice. And now the corresponding operator looks like this. On the site A itself, you have a Pauli spin flip sigma x, and on all the neighboring qubits of the site A, you have Pauli phase flips sigma z. And the stabilizer operator Ka is the 5-fold tensor product of these. All right, so now we know what the stabilizer operators are, and by way of the stabilizer equation, they define the cluster state. So that's all I had to say about cluster states at this moment. Let us proceed to experiment. So there's 2 early experiments. Of course, more experiments have been done, but I'd like to review 2 of the early experiments that have been performed in measurement-based quantum computation. So this is the first of them, and it was performed at a spatial distance of about 500 meters from where cluster states were invented, at a temporal distance of maybe 2 years. So shortly after cluster states were discovered, they were implemented. And the first experiment was with cold atoms in optical lattices. So this experiment was done by the group of Emanuel Bloch at Ludwig Maximilians University in Munich, Germany. So this first experiment only created cluster states and verified that they had created cluster states, but those states were not yet used for quantum computation. That was now done in the second experiment. This second experiment was done in 2005, so about 5 years after measurement-based quantum computation was discovered, with photons. It is an experiment in the group of Philipp Walter in Vienna. So in this experiment, they created cluster states of 4 qubits. They demonstrated a universal set of gates, and they even showed a tiny quantum algorithm, namely a Grover search with 4 items in the database. All right, so let's summarize for this overview lecture. So the subject of this mini-series is measurement-based quantum computation. We have now understood what cluster states are. We have looked at early experiments. The next thing for us to understand is how measurement-based quantum computation actually works, and we will see this in the next lecture.